It's my pleasure today. I'm Dr. Hayley Evers-King. I work here at EUMETSAT as a marine applications expert on the Sentinel-3 and 6 missions. And today it's my pleasure to introduce my colleague, Dr. Aida Alvera Azcarate from the University of Liège. She's a research associate in the Geohydrodynamics and Research Group, Environmental Research Group. She has a very, very wide range of experience in ocean applications of satellite data, having worked with sea surface temperature, ocean color, salinity, and various other types of data. She's also an avid tweeter, so if you're on Twitter, do follow her. She shares lots of really compelling images of our beautiful oceans all the time. But today she's going to be sharing a specific aspect of her work, which is about gap filling, a project that contributes to many parts of the Copernicus program, under which we do lots of work at EUMETSAT. So with that, Aida, the floor is yours. Please take it away. Thank you.
Okay, thank you, Hayley. Thank you very much. And thank you everyone for coming here today. I see there are a lot of participants, so I hope I made this interesting for everyone. So as Hayley said, I'm going to talk about filling gaps in satellite data, in ocean satellite data. I'm going to share my screen directly and just start the presentation. So, okay, so here's the first slide. So filling gaps in ocean satellite data. So as Hayley said, I work in the GHER. The objectives of this seminar is well, to give you an overview of techniques to fill gaps in satellite data using data-driven approaches. So approaches that are relying on just the data that are present. And this is for ocean satellite data. I will talk about, we will have 3 parts. I hope I have time for the 3. A description of DINOF, which is one of these techniques, data-driven techniques to fill missing data. A description of DINCAE, which is a neural network approach. And then I will do a demonstration exercise myself here, but I will give you all the materials if you want to try it at home. And this exercise will be with DINOF, with the first technique. So, in fact, there is a poll, as Hayley mentioned. So it's just a way of knowing a little bit more about you. So it's a little questionnaire to know what is your background. Do you know anything about oceanography or anything at all? Or do you know about remote sensing? Are you still there? I'm sorry. Oh, yeah, sorry, because it changed. Yeah, so you see the poll. Sorry, I saw a message. So there is we can see okay. So people more or less took already the poll. So we have graduates, searchers, and polls. I will give you a few seconds to fill it. It's very, very short, just to know who am I talking to, right? Because when we do a in-person seminar, we can at least see the faces and we see if people are lost with descriptions. So this helps also see what do we have in here. It's funny to see how this changed. Okay, well. Okay. So I don't know if we can also see the other, okay, all the others, career citizen, PhD students. Okay, good, nice. And yeah, knowledge about remote sensing. Okay, then that's really nice, good. And what about oceanography? Okay, so we have, nice. Okay, that's already good to know. I mean, it was just to have an idea. So we have oceanographers for the half of the audience almost, or acquainted with oceanography, and you have previous knowledge of remote sensing. So that helps me also continue. Okay, so I will reshare then the presentation. Okay, so now I know a little bit more about you. Now I will present myself as well. So who am I? I'm an oceanographer. I work with remote sensing data since almost I started my PhD, in fact. But in fact, I was born in Spain in the mountains. So what I saw as a kid was snow, high mountains, and things like that. So no ocean view. Then I very soon discovered the ocean and that I wanted to study it. So I've done a degree in marine science in Canary Islands. So this arrow here. Then I moved to Belgium to do a master, and to the master thesis I moved to Lisbon. Then I did my PhD back in Belgium, and then I moved for a postdoc to Florida, and then I moved back to Belgium. So Belgium has been my center of gravitation, so something like this. So from 2012, I have been in Belgium, in University of Liège, which is in the GHER. It's a group that makes research in ocean modeling and data simulation and the development and application of data analysis techniques like DINOF and DINCAE that I will explain today here. We also do a master in oceanography, and we organize the Liège Colloquium in Ocean Dynamics, if you have heard about that. So after being in Canary Islands, in Florida, in Lisbon, I ended in Liège, which doesn't have a sea view. So when I look up of my window, I don't see the ocean, but I can have amazing views from my computer screen using remote sensing data. So these kind of images, like the one you can see in here, which is a bloom in these turquoise colors, it's something that it's really very inspiring when you want to do research. So it's really something that really catch my attention every time I see something like this. So this imagery is what you see when you ask for ocean remote sensing. You see these kind of images. Now there is a little problem in it that these images are not always like this. So you see this beautiful. So you see the marble, the earth marble, and what I can see in this is the ocean, of course, the land. But what I see is clouds. There are a lot of clouds everywhere, and they hide what is happening behind them, so in the ocean or over land. So we have a large part of the ocean that is covered by clouds at any moment. And that's a little problem when we want to study the ocean from a satellite point of view. Okay, so I'm gonna move this, okay, like this. So we have a little problem, which is that the satellite sensors that we mostly use to study oceanography in the visible and in the infrared wavelengths, they cannot see through clouds or through dust or haze or anything that is too thick in the atmosphere will block the radiation and we will not be able to see it. So variables like sea surface temperature, chlorophyll concentration, suspended sediments, etc., are very affected by the presence of missing data. And there is, of course, a latitudinal and seasonal variability in the percentage of missing data. So yeah, you see the image in the left, which is what you dream of when you think of remote sensing data. But very often what you get is what you see on the right panel, right? So you really have only a part view, and there is a lot of missing information. Okay, so the clouds have always been a problem, okay, when we measure from a satellite. The good thing, or the good news, is that they move around. So clouds are not persistent, or not all clouds are persistent. They move and they go here and there. So they are today here, they might not be here today. So there are ways of getting rid of this missing data, interpolating the missing information, and have an estimate over points in which there is no information. So there are several approaches that can be used to remove or minimize the effect of clouds. One that can be just very simple is compositing, in which you will just put several images together from several days or several satellites, and then you have a mix of data. And because clouds move around, you will decrease the amount of missing data. The problem is that, of course, if you are mixing data sets at different spatial at different times, you can have gradients. I chose this one, which is, yeah, you can see really gradients. You see this little jump, this kind of, do you see my mouse, in fact? I'm not sure about that. Hayley.
Yes, we do, Ada, it's fine.
Okay, good. So I can move the mouse and you see, okay, so you see these gradients. This is because you put several images of several sensors or several days together into one, and then you can have some artifacts, some gradients that are not realistic, or if you are averaging, which is also a way, then you will lose in spatial or in temporal resolution. You can do a composite of 8 days, then you will get rid of many clouds, but of course you only have one estimate every 8 days and not every day, for example. So compositing is an option, but it has also its downsides. Then there are interpolation techniques, and there are several approaches, but the one that is most known is the one called optimal interpolation, in which we have a field that is the result of a first guess and a first average value of the field, and then a weighted sum of the observations. The little problem here is not a problem, but you need to know how to weight the observations. So you need to have some previous knowledge of the characteristic of the field that you want to interpolate. For example, the correlation length. So how big are the features that I'm trying to reconstruct, how large they are. So this kind of analysis, optimal interpolation, etc., they are based on a model or on a previous knowledge, or some kind of knowledge that we have about the medium. So this can lead to subjectivity in the estimates. Again, they are very useful, and they are, I mean, you can find a lot of estimates of interpolated satellite images using optimal interpolation, and they are really very fine. But that's not what I do. What I do is use data-based techniques. So instead of having some function behind that will tell me how the observations can be weighted and how large are the features, I want to rely on what the data themselves are representing. And that's the idea of the data-driven approaches, like DMF. Okay. This is going to be a little maybe more technical, but I hope I will make it clear to everyone. So we started with these data-driven approaches, so approaches to interpolate missing data based on what the data have themselves. In this work here in Bergers and Rixen in 2003 at the GHER. And what we aim to do is to develop a method to estimate missing information from an EOF basis. EOF is empirical orthogonal functions. In order to calculate an EOF basis, you use what is called an SVD method. So that's a singular value decomposition. So before going further in there, I will stop for a minute. So SVD, so singular value decomposition, and all these techniques, PCAs, EOFs, this goes back to algebra lessons that we had in high school, and there are lots of really great resources. You can just search on YouTube and you will find really a lot of lessons. I particularly find these ones very nice. So you will have access to this presentation. You can just go and see this link. There are like 20 lessons on singular value decomposition, but already the 2-3 first ones are very introductory and really give you an idea of what this technique is for. So this is a mathematical technique, okay? Not if you're interested, I suggest you go looking for this kind of lessons. So we will just concentrate on the EOF, so the empirical orthogonal functions. And that comes the second question in the poll. So have you worked with EOFs or PCAs before? So if you can go to the poll and maybe answer that question. I will stop sharing this and see. I don't know if you have. The poll in there. Okay, 50-50, more or less. Okay. Then. Yeah, I think we're 50-50. That would be okay. So I can share again my screen and continue a little bit. So EOFs, I will describe a little bit what EOFs are. In fact, EOFs, empirical orthogonal functions, it's a compact way of representing the main modes of variability in a data set. So imagine we have C-surface temperature, like the one you see in the left image, and it's changing in time and in space. So you have a lot of variability, a lot of scales, long scales, shorter scales. So there is a lot of things going on in there. Well, the EOF empirical orthogonal functions will decompose this three-dimensional field in a series of spatial and temporal modes in varying order of variability, in decreasing order of variability. So the most important mode will be placed first, then will come the second mode, etc. And what is a mode? So this is the first, so we have this, time series in here, which is C-surface temperature in the Black Sea. It's an excerpt from a 1 year data set. Okay, so it goes from January to December 2018, in fact. And I'm just showing here an event that took place in August. I'm sorry you don't see the dates, but in August we had an upwelling, so a little cold water coming into the western, in the eastern part of the basin, and then moving to the west. Okay, so that's just one event that happened in August, but the data we want to analyze here is a 1 year time series. So the first mode, in fact, because this is temperature, will be the annual cycle. It will be cold. You see this time series below. It's cold in winter and it's warm in summer, and then goes back to cold. And when you look at the spatial distribution, it says that the amplitude is larger in the northwestern shelf, which is shallow, and because it's shallow, then the amplitude of the signal is stronger. So it hits more and it cools more. So it's warmer in summer, it's colder in winter, and the same thing for the Sea of Azov. Sorry. So this spatial mode tells you how the temporal variability changes in space. Okay, so yeah, we have this first mode is just the annual cycle, summer and winter. This is the first mode. And you can do the same thing for next modes. We'll be capturing the other kinds of variability that is found in the data set. I won't show you all of them. I will just show you EOF number 8, which in fact captures this upwelling that we were seeing in here. And then you see that it's very variable, but it peaks in August. Okay, so the highest value of this upwelling comes exactly when it happened, which is in August. Okay, and then the farther you go in the EOFs, the smaller the scale. So you see EOF 14, it has a much finer scales in this representation than one we had in the first mode, which was quite smooth. Okay, so this is just a way of hierarchy organizing the variability in spatial and temporal modes and in order of importance. And in fact, the first mode, which is the annual cycle, represents already 96.68% of the variability, which is quite a lot. I mean, a full year of SST in the Black Sea, so 1 image per day, and all these pixels in space, can be, so 96% of the variability can be summarized in 1 image and 1 time series. That's 96% of total variability. The EOF8 that represents this upwelling, which is quite large, and I mean, it's not something minor, I would say, that's only 0.03% of the variability, because yeah, in comparison with the annual cycle, it's really very small. And the EOF14 that I put as an example is just 0.01% of variability. Okay, so this EOF is a mathematical tool to extract the main variability and put it in a decreasing order of importance. So in fact, it's very effective to compress information, because yeah, you can, instead of having 365 images for a year, you might have 14 images and 14 time series, and you will be around 99% of the total variability already contained in there. So EOFs are used for compression and for extracting the main information. So I come back to this slide now that I have explained the concept of EOFs. So these EOFs will be used for in our technique to infer the missing information. So this information that it's not there because of the presence of clouds. Okay, and as I said, we use an SVD, but that's not important now. The only thing in here is that EOFs, in fact, they should not be calculated when you have missing data. In fact, it's a tool that you can use very easily with complete data. But if you have missing data, yeah, mathematically is not optimal, I would say, because the main problem is that the matrix that is being classified, you can no longer attribute the importance of the modes. So you cannot longer say what is the most important mode, the second one, the third one. That's not possible or not optimal to do. So you cannot longer organize this EOF. So you cannot work with missing data in your EOFs. So we are, in short, calculating EOFs that shouldn't be used when we have missing data to find the values of the missing data. So how does that work? So that's the principle of DNOF. So this technique we developed for missing data. DNOF stands for Data Interpolating Empirical Orthogonal Functions. And this is a diagram that shows you exactly the steps. So you take these steps, you could change that to code and you will obtain the code of DNOF. Okay, so this is really what it's being done. We have our matrix with missing data in them, and we want to reconstruct things. So the first thing we do is missing the data flag, flag the missing data, and set them to the average value. But as we are working with anomalies, so we demean the matrix, and the missing data will be set to 0. And at this point, before starting calculations, we will set some data aside, so some valid data, some present data, and we will mark them as missing, so that later we can see what DNOF is doing, suggesting for the reconstruction for this data, and compare them with the real data that we have hidden from DNOF. Okay, so that's the cross-validation. Okay, so once we have this three-dimensional matrix, so space and time, we will ask for the first EOF, just the first one, the main one. Once we have this first EOF with, again, zeros in the missing data, so a very bad first guess. Once we have the EOF, we can use this SVD to recalculate what is the missing, the value at the missing positions, because we now have an EOF basis that describes the matrix. So we can recalculate what the value is for the missing positions. So we have an improved first guess for the missing values that we re-inject in our matrix, and then we calculate the EOF with this improved guess for the missing value. We will obtain another EOF, and then we re-inject the values, and so on, until we reach convergence, until doing more iterations doesn't change the value that I obtain for the missing points. So at that point, I have the best value for the missing data using just one EOF, and I will calculate a cross-validation error. And then I will put my error somewhere. Okay, so this is my error with one EOF. Next, I do the same thing, but with the two first EOFs, so the two most important modes of variability. I calculate the missing values and then improve the guess and reiterate until I have a convergence. And then I calculate the cross-validation error. And again for 3, and so on. So at the end, I will have a curve of errors. So that tells me the error that DNOF is committing by calculating missing values using just one EOF, 2 EOFs, 3 EOFs, etc., on the points that I know the value, the true value, right? So that's why I can calculate this error. And at a given point, I will reach a minimum, because adding more EOFs will start adding also very small features like noise and errors in the data that can be present. So adding that will in fact increase the error instead of decreasing it. So at one moment, adding EOFs will increase the error. So I know what is the optimal number of EOFs that will reconstruct my data set. And then I can do a last reconstruction with this number of EOFs, and then I will obtain the best thing I can do for the missing values using DNOF. Okay, so that is the basic functioning of DNOF. this slide more or less repeats things, but I will just make sure that it's clear. So DNOF is a technique to fill missing data, to interpolate missing data, and it's based on a NeoF decomposition. The missing data is initialized to the mean value, and then we calculate anomalies. Then the first guess, because it's just zero, just the mean value of the matrix has a very low accuracy, but an incremental and iterative calculation of EUF modes allows us to improve that and get to the best result. We are using a truncated EUF basis. That means I'm not using the full series of EUFs that I could use. I just stop whenever I reach the minimum of the error to calculate the missing data. That helps reduce noise and some bad data that can be present in the initial satellite data. But the downside is the variability, and some small scale features can be also be reduced because they are also filtered out. Okay, and the optimal number of EUFs is calculated by cross-validation. At the beginning, 2 to 3% of the valid data, of data that are really present, I will just put them aside. And to do that, what I do is to put them in the form of clouds. So instead of just hiding random points, I will hide them in clusters in the form of clouds, because that's more difficult to reconstruct. Okay, so it will be more realistic if I have an idea of what the reconstruction error is when I put a cloud. And then I can have an error estimate for each EUF. And this is the kind of reconstructions that you can get for DNOF. So in the left image, you have an initial data with missing points, which are in white, and then the reconstruction in the right. But again, this is one snapshot on a 3-dimensional data set. So DNOF is able to get this missing data because there is spatial and temporal information, because clouds move around, and sometimes I have missing data in one part, but then it disappears, and then we can take advantage of this spatial temporal correlation to have the missing data. The benefit of this kind of approaches is that it's non-parametric, it's data-based. So it is the data that are dictating the scale of the features that can be reconstructed from the data that are there. Okay, so it's just a little bit as if we would do it like by hand. So we see there is some kind of eddy in here in the middle of the Mediterranean Sea. This is surface temperature again, and we see the eddy sometimes, and then it gets hidden. But we know it's not disappearing; it's still there. So whenever it's not there, well, the eddy should still remaining there, and that is what DNOF is doing, trying to get the spatial and the temporal information to infer the missing data. Okay, I think I've mentioned everything in here. Okay. So, as I said, there are downsides of using a truncated EUF basis, so not using the whole EUF basis that we could calculate. The advantage is that you see these little points in the left image, like a little call. So these don't look as realistic. Well, these are filtered out, but you can also have the intensity of some of the image of some of the features might be also not there, or even you can really have them completely filtered out if you if there is not enough information. And in fact, I wanted to have a word on resolved scales and how to reconstruct that. And for that, I have a little poll. We are going to have a little game. We are going to play join the dots. Okay, so I know everyone, or almost everyone, has played this. You are given a hidden image, and you have to infer what is in there by joining by the information you have, which is the dots and the order. Okay, so given this image, you have to do your best and estimate what is the hidden feature. So there is a little question in the poll. I would like to see what you say. What is this hidden image? So can you please go and vote? And we'll under measure, again, measure apple. Okay. So yeah, wow, we even have the icon. Yeah, I'm the ocean, yeah. Okay, so I think we can say it's an apple, right? Okay, it's an apple. It looks like an apple. I will share my screen again. It looks like an apple, right? We just, with the information we have, we can just go from 1 to 2 with a smooth line, like, right, not straight, but just a little curve, then go from 1 to 2 to 3 to 4, etc. And so the answer would be, well, this is an apple, right? But what happens if, in fact, we had clouds in here? Well, in reality, there are no clouds, but there are clouds that are hiding, in fact, what is happening between 2 and 3 and between 3 and 4. And we are, in fact, missing a lot of the variability, so that we are not able to reconstruct that. Maybe what was being sampled here was a rambutan, okay? So, in fact, the message here is that we are only able to reconstruct what we have enough information about. Of course, this cloud was very strong because it was hiding all the spikes. Normally, clouds will hide some of the variability, and some of the variability will be there. So you still have some information, but yes, you are only able to retain scales that are sufficiently represented in your data. So if you have a very fine scales scene that is appearing just half, because half is covered by clouds, and then it just lost in a sea of clouds. Those scales, it's very difficult that they are retained in an interpolation technique, because the variability, the representativity in the full data set you're trying to retain is very small. So you will be losing all the spikes, all the very small variability, because they are insufficiently represented. So it was maybe a rambutan, but we don't have enough data to confirm that. Okay, so yeah, that's a little game. And this is a beautiful image I had recently, and then you see really that the ocean, this is surface temperature in the Gulf of Lion, and you see that the ocean can really have very small variability, fronts, eddies, and things that are really like wavy patterns here. You see a front that is unstable and starts to break. So it's really all this variability. If the day before and the day after you have a cloud that covers it completely, well, it will be very, very difficult to retain all these scales in a final reconstruction. Remember that we have a lot of clouds in the Mediterranean. We have about 50% of clouds in average. And if you go to other areas, it's more like 70%, and sometimes it's even higher. So 70% of your data is typically hidden behind clouds. So you won't be able to have a rambutan, you will have an apple. That's the message. Okay, now up to here, what I have described is just the vanilla method. So the DinoF as it was first thought, and it's completely parameter free. So you really have your data, and DinoF decides on the reconstruction. So you don't have to have previous knowledge, or you don't have to establish a scale of variability that will be the one that is retained the scale of variability that is given to the reconstruction. You don't have to infer any of that. And it's parameter free and data driven. Now, we have done some small additions that have some parameterization, some things you have to really work with that lead to better results. And I will just briefly describe two of them. First is the temporal coherence of the reconstruction, and then I'll go to outlier and shadow detection. So for the temporal coherence of the reconstruction, in fact, one thing about EOFs is that they are not, how to say, so they are not ordered in time. So you have a three-dimensional matrix with 1 year of SST or chlorophyll or whatever, and you shuffle all the dates, around. You still have the same data, but just disordered in time. Well, the EUF basis will be in fact the same. Okay, so the data are the same, so the EUF will be the same. So the EUF don't know about the sequence of the data. They don't know that 1st January comes before 2 January. And so what happens? Sometimes if you have very few data, that can lead to some problems. So this is an example. I have here a time series of SST in the Black Sea. This is again, I think it was 6 months or something like this of SST. And these 3 days were consecutive days that had data. So 24 December, 25 December, 26, there was no data at all. So it's not here. So from 25, we go to 27. What happens? In 24 December, we had like half the Black Sea covered with clouds, and the other half was more or less visible. And you can see here the Batumi eddy, which is this one here. You can see some cold data, etc. The next day, in fact, almost everything was covered by clouds except for this little strip of water in the east. And the next day, which was 2 days after, it was just the other side of the Black Sea, which was this cold water mass in here. DNOF, just with that information, again, this is just 3 snapshots from a 1 year data set, but with that information, the only thing that it can do is to say, well, from here we go to a warm event and then a cold. So it proposes something like this. It proposes that from this reconstructed image, we go to this image, which is like 13, 14 degrees. And then the next day, we are like 8 degrees Celsius. Okay. This, we know that is not possible. We cannot have a change in temperature that goes up to 3 degrees and then down 6 degrees in 2 days. It's not physical. But for DNOF, with the few data that was there, to constrain the EOF, it was the only thing that it could do. So if we could have given that these images were following themselves, then we would say, well, yeah, from here, it has to be something like more similar to this, right? And so on. And we did that by adding some kind of filter to the covariance matrix. So the covariance matrix is the matrix that is used for the calculation of the EOFs based on the data. And you can see that there are some stripes in there, and these stripes is these jumps that we have seen in the image before. So these jumps are there because there was not enough data. So if you filter this matrix, so this matrix is the data matrix transpose times the data, okay, X transpose times X. If you filter this matrix, you obtain a smooth version in which the jumps are not so evident. So this is the filter that is applied to the covariance matrix, F transpose times C times F. It's a Laplacian filter, like a Gaussian filter, but just two-dimensional. The filter is made on the covariance matrix because it's much smaller, so it's more efficient and it's less sensitive to missing data. And we can apply the filter iteratively. So more iterations, the farther you reach. So the more you filter, the more you smooth. Okay, so what is the effect of this filtering into the reconstruction? Then we have the third line in this image. Okay, so then we have a sequence of data that is much more physically plausible than the one what we are obtaining in here. So in this filter, so this results was obtained using a filter of 1.1 days. So you don't need really to filter very strongly. Just a short filter will do enough to obtain a much better result. So this is something that you have to, we have to add to DNOF if we want, but it leads to really very good results. So I always use it by default, in fact. Okay, and then the other developments, I would just mention the outlier detection. In fact, because we are working with an EOF, we can use this EOF basis to see how different any pixel is from the EOF basis to the initial value. So if we have an outlier, it will be very, very different from the EOF basis used in DNOF because we are truncating, okay, the EOF basis. So our EOF basis will serve as a what is the expected value of a pixel. So pixels that have very different values are suspect. So we have an initial data here. This is surface temperature in the tropics. This was with the TMI sensor. And you see that the water is like 28 degrees. And then we have some red spots that are just points that were not well detected because they were close to clouds and things like that. So they were just undefined clouds, something like that led to very strong values and then erroneous values in the initial data. When you look at the EUF, the difference with the EUF test, you can see that these points already pop up, but we added some other tests like a local median. We just took a little box of 20 by 20 pixels and you calculate a median. And then if you are too far away from that median, that's also suspicious. And then a proximity test in which if you are close to a cloud, you are also more suspect. So by combining these three tests, we can decide which points are suspicious and should be let out, should be taken out of the image before doing the DNF reconstruction. Okay, so that allows us to detect and remove detect and remove outliers efficiently. And then you have to decide how much you want to, how strong you want to detect the outliers. So a higher threshold will be less strong, and a lower threshold will be more strong. So again, these are additions that need some parameterization, but you can end up with an input matrix that is much less noisy than the initial one. And yeah, I had also this one because again, with the EOFs, we also can detect non-physical signals that can happen sometimes because they are detected by specific EOFs. And this was an example we did with the SMOS data, salinity data, in which the edge of the swath was doing some kind of strange noise, error structure in the data. And this was captured by two EOFs. By removing these two EOFs, we were able to really remove that signal from the data. So that's some of the applications that can be done in addition to the missing data reconstruction. And then last of the additions that I wanted to show, this is similar to outlier detection, but it's the shadow detection. And this is very useful for when working with very high spatial resolution data, which has like Sentinel-2, for example, which has a 10-meter resolution, and in which you resolve very well the clouds, and then the shadows are also well resolved. So they are contaminating your data set. Again, a combination of tests, mainly the EOF basis, plus other tests allows us to detect the shadows and then remove them before continuing with the analysis. Okay, so that's two examples, one in here, in which you can see the clouds, how they have been detected. So the cloud shadows, sorry. So yeah, so in short, to end up just the first description of DNOF. So DNOF is a reliable method for filling missing data. It has been developed, used, and improved for many, many years. So we started with this in 2003. And we have several applications for data quality improvements that have been developed around DNOF. This data here shows the chlorophyll concentration in South Atlantic. So you can see high values near the western part of the Atlantic, sorry. And you can see all these swirling eddies and things going on over all the Atlantic, and they are in the panel below, they are reconstructed by DNOF. Again, because the clouds move by and because the filaments and the eddies are quite persisting, they are there, they move around, but they are almost always there, we are able to make a good reconstruction with DNOF and retain this variability. Okay, so that's for DNOF. Before moving to the DINCA part, I don't know if you have specific questions. Maybe is there something in the slide, or there is a question and answer. So if you have any specific question about DNOF, maybe it's better to ask them now, and then we can maybe go to the rest of the
Ada, we've got a couple of questions I can
Okay.
tell you. Oh, you can see them there. So
Yeah, okay.
here, have a look, see if there's any there you'd like to answer.
Okay. So that's the first one, right? Is this only used for satellite data, or can we use it for ground-based data? Yeah, so it can be used for time series. Now the technique itself has been coded for three-dimensional data, okay? So in fact, what I have been doing sometimes when I do some reconstructions of time series is to reshape the data in order to have them in three dimensions. So in fact, maybe you have several positions, several locations in which you have data, or yeah, you have to reorganize your data to make them into a two-dimensional matrix. But it can be done. You need a lot of data as well. As if you have just 30 points, then it's not. I mean, you can do a linear interpolation or a cubic interpolation. That will be enough. But if you have a lot of in situ data that have missing information, then DNOF can of course be done. Is DNOF incorporated in the Siemens data sets? Yes, well, there is several things. There is a new product, the high resolution ocean color, which is a Sentinel-2 based ocean color data in Siemens, which provides a level 4 data set, and that one is done with DNOF. Okay, so that's for the very high resolution. I think it's 100-meter resolution, and it's just for the coastal regions. Okay, so really the 20 kilometers from the coast all around the Mediterranean and all the European seas, I think. So that's for the Sentinel-2. And then there are level 4 chlorophyll in Siemens, which uses a modified DNOF. So they use the concept of DNOF, but they applied something a little different. Some modifications. So it's based on DNOF, I would say, but they have their own modifications in the data set. How can we apply the DNOF method? It's possible to do it in R or Python. Can you share the code? Okay, so yeah, that is coming in the third part. So the code is available. If you look, I will give the address later, but you look for GitHub DNOF, and then you will find the code. It's there, it's available, it's open. You can download it and just use it, no problem. I'm happy to have people using it. So the code itself is written in Fortran. Okay, so you have to, you have. I mean, I provide. I'm not sure if in the GitHub I have the executables, but I will provide you later with some, just the executable, the binary from DNOF, so you can just run it. You don't need, in fact, you don't need to go into the Fortran code. Now, what I will be showing after finishing the talk will be some notebooks. Now, the thing is that they are not in Python, they are in Julia, but that's a language that it's pretty neat. I like it. And we have ended up working a lot with Julia here in the GHER. But I mean, if you understand Python, I will just drive you through the notebooks anyway, and you will see that it's pretty easy to understand. So I will give you some notebooks that you can try to apply DNOF at home. Okay. How long are the time series you recommend for the EUF analysis, and how are EUF and the reconstructions affected by trends? Okay, so so how long, that's something that you need trial and error. Okay, so typically I would say the longer the better. Now, if you have a very, very long time series, you will have two things. First, it becomes computationally very heavy. So yeah, it's maybe not ideal. And also too, if you have a very, very long time series, DNOF will give a lot of weight to just the interannual variability. So the annual winter and summer, or the spring bloom if it's chlorophyll or something like this. And the small variability will start to be like just too small to be retained. So that's something, there is no simple answer to this question. That's something you have to try and to see. what is better. What should I do with my data? Should I use it all at once, or cut it in chunks, maybe once in for a year? I would say 6 months is for SST, for example, 6 months in a given basin in the ocean. It's more than enough. So that's a typical length that I use myself. But again, it really depends on the data and the amount of noise, the amount of missing data, the variability in your data set. Maybe you are in a region which is very complex and has a lot of variability. So maybe it's better to have a little more information. So it really depends. But yeah, it's something that comes with practice. And the EUFs, well, they will reflect these trends, of course, if they are present. Now, again, I typically don't do like 20 years at once. I do like year by year for the reconstruction. So you wouldn't have this global warming or sea level rise trend. You won't have that as a very strong trend in your data. They will still be short. But again, yeah, it depends. Now, one thing that I can mention also is that a 6 month or a 1 year data set in the Western Mediterranean or the Black Sea or whatever, it can run in my laptop in a few hours less. I mean, it's really fast. That's something that is interesting to know as well. I mean, you don't need a supercomputer to run the EUMETSAT. Okay, and thank you. So if I understand correctly, only when we have a time series of satellite data, we could use enough to look up, since it wouldn't work if we are purely working a single image. Yes, you need the time series because you need the spatial temporal information. If you have an image in the Western Mediterranean, or let's change, okay, in the Caribbean, and you have a cloud that is hiding a filament, if you only have one image, there is no way DNOF can know that there is a filament below the cloud. So yeah, you need a time series in order to really get this information. And next, do we have to manipulate the data in any way if the variable to reconstruct, yes, is log normally distributed and normally, yes, that's a very good point. And whenever I work with chlorophyll, I work with the logarithm of the variable. So all variables that have this kind of distribution, so no negative values and then a lot of values near the small values and then less, so this distribution, then you do a logarithm to make the DNOF reconstruction, and then you redo the exponential. Yeah, that's because DNOF expects a normal distribution, of course. Okay. I missed this from the beginning. Is it going to be recorded and distributed? Yes, I think so. So I think that's solved. What is the furthest you have pushed in EFID, especially or temporarily? Have you reconstructed over a very long time series or over a very large area? Yes, there is a number. I don't remember what the number is, but there is a very large number that is like the limit. I have to check that, but well, whatever. I have done reconstructions with Sentinel-2 data, which are 10 meter resolution, and I was doing them over 1 year in a region in the Belgian coastal zone. So it was, the matrix was, I don't remember, it was maybe 10,000 by 10,000 pixels and then 1 year of data. It's Sentinel-2, so it's not every day, but I mean like 80 days. And yeah, no, that doesn't work. It's just too much. I mean, it doesn't, sometimes it doesn't make sense to really go so big because, as I say, if you have too much information, the small variability is also sometimes lost in the UF basis, and then you lose that. So yeah, the latest I've been working with a very large data set was a 23-year reconstruction of chlorophyll in the North Sea. In the North Sea, really up to the Faroe Islands, really very big. And I cut that in years, just every year separately, because it's just too large. And then you will end up just with a very smooth reconstruction, just giving you the long variation. So yeah, it's better to cut things in pieces. In which area DNF gap filling method is most useful? Numerical weather prediction or operational forecasting, climatology, commercial pictures. Okay, so I use DNF for research, right? So I have my data set that I try to have the best data set possible with as less noise and less bad data as possible, and you create that, and then you will obtain the best thing possible. So it's like in research mode. I also have a demonstration webpage in which DNF is run every day for the Western Mediterranean Sea and shows the latest reconstruction just for yesterday, every day. That's operational, so it works alone. I don't touch anything, and every day I have my latest SST. The thing is that it's good for the purpose of having the best estimate you can have for yesterday, given the data you have. But again, if you have, for the last day of your data set, you have a filament that starts popping up, and it wasn't there before, it's very probable that your last day won't show that filament very strongly because it doesn't have enough weight to be retained by the EUFs. So for operational use, it's okay. It's like, well, you do the best you can with your data. But once you want to study that filament in detail, then I will suggest to go back and take the data set that contains the whole development of the filament so that you have it in your data and you can do the best reconstruction. But it can be done. It can be used for operational data. Could DNF method be applied also to the gap filling of land remote sensing time series? Yes, yes. It's just for a geophysical data set, for any, I mean, for data. It can be whatever data. Of course, it depends also on the data and the variability it has. Maybe there are some specificities for some variables that I cannot imagine now, but I can see it very well to be used in reconstruction of, I don't know, NDVI in the overland, also atmospheric variables like aerosols or things like this, or dust. It can be done. I'm not sure about the results because I haven't done myself, so I'm not sure, but there's nothing that refrains enough to be used in the overland. Yeah, of course. Mm-hmm. And if someone in the audience does this, I would really love to see how is it going, because I'm for a long time I've wanted to really do a land application, but I just don't have the time for that. So if anyone tries, I'll be happy to look at that. So how quickly can DNF adjust to a very dynamic, genuine change? If an eddy moving 10 kilometers a day on a daily 1 kilometer sequence. It depends on how much data or how much missing data there is. Okay, so if your eddy moves 10 kilometers a day and half of the days it's not there, so it will only be seen 20 kilometers away. So that can be tricky. Yeah, I don't know. You saw the image that the animation I saw at the end with this South Atlantic chlorophyll. You see those eddies. I mean, they move around, but they don't move 10 kilometers, right? Yeah, I don't know. So maybe 10 kilometers. I mean, it depends on the missing data. It all depends on the data, in fact. So yeah, that's something to try. If you know of such an eddy, I would love to give it a try. Okay, is there a summer course or more detailed course we can attend on this subject? I mean, not for now. I haven't anything on my agenda. Now, this is something, if there is enough, request or enthusiasm from the public, we could maybe one day try to organize a little summer school or something. That would be very nice, very funny to do. Yeah, if I do that, I will announce on my Twitter, for example. So just keep an eye in there. Have you validated the outputs of DNF with the institute? Yes, that's something we always do. So whenever you do a reconstruction, you try to find in situ data that will allow you to determine the error. So we have the cross-validation error, of course, but that's only, I mean, we're using the same data that we are reconstructing. So it's always a good idea to have it checked with in-situ data, on the independent data. Yeah. We want to apply this method, not theory only. Yes, I will show you a notebook. We won't do it like live with you, but I will give you the notebook so that you can try it home as well. Can we use this method with wind and wave height from satellites? Yeah, the only thing you need for one thing you need for DNOF is having gridded data. So you need level 3 if you're familiar with that nomenclature. Level 3 data. That means level data on a regular grid. So every day you will have the same grid, and that is repeated with time. So yeah, even if you have missing data, but the grid stays the same. So that's the only thing you need. But if for wind, it will work. For wave height, yeah, it depends on the data set you are thinking to use. But yeah. How do you find sufficient amount of data? Yeah, that comes with practice, I'm afraid. So that's something you really have to feel with the data set and try around. So yeah, that comes with practice. I mean, as I say, for sea surface temperature, 6 months. That's a good compromise, I would say. Can we use it with atmospheric data as well? Yes, I already said that. So yes, that's something we can do, and I will really be happy to hear people doing that. Can we benefit for a grant for training in remote sensing? Yeah, I don't, not rightly from me, but maybe Hailey has some some contacts or information about that. Well, in the University of Liège, it's not remote sensing, it's oceanography. We have this master's in oceanography, and some of them are in this Erasmus Mundus framework. So that's a way, of course. So that's but then remote sensing will be just one or two lessons, of course.
Yeah, I can add to that. Aida, we do offer some funding support for people to attend trainings, not so much at the moment because we're all doing everything online, unfortunately, thanks COVID. But generally speaking, we do. There's also opportunities at EUMETSAT to do things like internships, and there's various research positions and things that get advertised. Those are more on our main website and our vacancies. The training, you can look at training.eumetsat.in to see what's going on there. But yeah, happy to talk to anybody more about these opportunities too.
Yeah, that would be nice to know. Okay, another question. So what do you think about usage with discrete data like storm? So again, if you have really just one thing that pops one day and then it disappears completely, then yeah, there's really a high probability that it just not retained by DNOF. Now, if your storm, let's imagine a wind, for example. So you start having a wind event that develops and then gets stronger by the day, and then one day it dissolves. Then you have several days of this storm, and you could imagine that having a time series that contains this storm, then you will have it, of course, in your data set. But again, if it's just one on and off event in a full year or 6 months of data, then yeah, maybe it's not enough. But I mean, a storm, it's several days typically. So yeah. One thing we can see, which is nice, sometimes you see the cold wake of hurricanes over the Atlantic, right? When you have this hurricane extracting the heat from the ocean as it goes by, and you have this cold wake behind, and you see more or less in the SST, infrared SST, and DNOF is also able to retain that as well in some tests that I have done. So that's yeah, this kind of events are possible to retain, of course. But again, it's something you have to try. You have to really see your data. Okay. Nice, that was a lot of questions, good. Right, so I will go now and explain Dinkai. The Dinkai part, it's shorter because yeah, I don't think I will have time to really go a lot into detail. So we'll explain this neural network part, and then we'll move to showing you the notebooks. Okay, so that I think that would be nice. So there is the fourth question. So have you worked with neural networks before? In the poll, if you can answer that, I can see. Wow. 50, okay. 50-50. Okay, okay, there's still a good amount of people that have worked or that know what neural networks are. So that's nice. Okay, good. Then I can go on, share my screen again. And yeah, so we'll talk now about, sorry. So another technique that we have developed here at the GHER, which is called DINCAE. It stands for Data Interpolating Convolutional Autoencoder. So yeah, you realize that we like DIN at the beginning of our words. We have DINOF and then DINCAE. So the objectives of this technique, this is something we have developed much more recently than DINOF. So this has been developed over the last 2-3 years now. Yeah, more or less. And the objective is, as for DINOF, to derive a methodology to reconstruct missing information in satellite data. At this time, instead of using EUMs, we'll be using neural networks. The use of neural networks, as you are well aware, I think, has become really very widely used. So they have been really very widely used lately because we have so many data now. We have accumulated several decades of satellite measurements, and we have computational capabilities to do that, to really ingest all this information. So that's why they are really exploding now and being really used everywhere. So we also, as before, want to retain small-scale variability as much as possible. Okay, and then we will compare. We have compared it with DINOF to assess the quality. So the data, so I will show you just an example on how it was applied. So the data we have used for this example was the ADHR surface temperature data at 4 kilometer spatial resolution in the region shown here in orange, and that's the Ligure-Provençal Basin in the Western Mediterranean Sea. And so we used 25 years of sea surface temperature, in which there were 47% of missing data. Okay, and yeah, you have winds. So this is an average sea surface temperature. You have cold winds that come over the Gulf of Lion that make this cold feature here. Then you have a cyclonic circulation going from Corsica to the coast of France, continental France. And yeah, that's the region we want to reconstruct. And this is the data. Okay, the challenge is for a neural network to train on GAP data. So as we were mentioning before, EOFs are not conceived to be working with missing data. Well, neural networks and training of neural networks typically don't expect missing data either. Okay, so that's something we have to come up with an idea to deal with that. Okay, so what we have developed, so this DINCAE stands for Data Interpolating Convolutional Autoencoder. An autoencoder is a kind of neural network that is used to efficiently compress and decompress data by extracting the main patterns of variability. I don't know if that sounds familiar. That's exactly more or less what the EOF do, right? Now, EOFs are let's say the linear companion of the autoencoder. So autoencoders are able to retain nonlinear relationships between the variables we're working with. But the idea behind is quite similar. Okay, so the autoencoder is extracting the data, extracting the main variability in the data set. And why convolutional? Because it works on subsets of data instead of all the data at the time, so that we can concentrate on local features. So that's why we are using a convolutional autoencoder. Now, the missing data. So again, an autoencoder is not expecting, or a neural network is not expecting missing data. So what we have done is think, okay, if a data point is missing, we will estimate that the error variance tends to infinity. And then as input for the neural network, instead of using the variable, in this case the SST, we'll use the variable divided by the error variance. so that if it goes to infinity, then it will be 0 for some points, okay, and then 0 variance. So we're using the variable divided by the error variance, and that allows us to put missing data in there and indicate that they have very large error, okay? So you shouldn't trust the missing data. So the autoencoder uses the variable SST, the error variance, or the inverse of the error variance, longitude, latitude, and time in it. And this is the structure. So it has an encoder part, a bottleneck, and a decoder part. The encoder part is the one that extracts, so extracts the main variability, and then the decoder get back to the initial resolution of the data. So we have 5 encoding layers in which we have convolutional filters 3 by 3 applied at each layer, and then 5 decoding layers. We have also added some average pooling layers. This is to reduce the size. So we every time we reduce the size by averaging over 2 by 2 boxes, so that allows us to, in each step, reducing the size up to the bottleneck. And the decoder layers are upscaled by nearest neighbor interpolation. So again, you extract what is the most important information, the more important information, and then you reinterpolate that into the initial grid. Now, in order to really concentrate on the small scale features, we also add some skip connections, which means the information which is in here is also added back at the end, so that the fine scales are not lost in the bottleneck. Okay, so you just put this information back after the bottleneck. So that's the baseline method. I mean the Dinkai method, and we compare that to DNUF, which I just explained before. So for that, we have this 25 years of data, okay? We have partitioned for the training. So yeah, sorry, for the neural networks, we have a training data part and then a prediction part, okay? For the training, we partition the data into mini batches of 50 images. And then the entire data set is used multiple times, like thousands of times, which is called an epoch in neural networks. For every input image, we, in addition of having the missing data we had, we added even more the data points mask for the cross-validation error. And yeah, using a cloud mask. For the output of the training neural network is a Gaussian probability distribution, okay, like has this form in which we have the error between the estimation and the real data, and also a function that penalizes if the standard deviation is too high. Okay, so that is the Gaussian probability distribution that is used to later predict in images which have not been used for the training. So there are 2 steps. One step, the training to create this function, and the second step, the prediction, in which with this function you can predict or estimate what is happening below the clouds. So some results just to show how things work. For the cross validation, we remove the last 50 image of the time series, and then we try to reconstruct that. The blue line here shows the error of Dinkai. So you see that it really varies a lot. This is epoch, so each iteration, each try. Now the turquoise curve shows the DNUF error. And in fact, when you, instead of just using a single epoch, a single iteration for the neural network, if you average specific epochs, you can in fact decrease the error, and then you end up with the red line, which is lower than what was obtained by DNUF. Okay, so we had a DNUF error of 1.17 degrees Celsius, and with Dinkai we were to 1.14 degrees Celsius. Okay, so it was about a little lower than DNUF. And here's some examples of reconstruction. These are the original SST. Then we added some clouds to make the neural network predict that. And this is the reconstruction we obtained with DINCAE. Now we also obtained an estimation of the error, which is lower in zones in which we had initial data, right? So that's, you can see that it matches pretty well the mask in here. And then we compare that to a DINOF reconstruction. And this illustrates quite well what I was talking about having two long time series. In DINOF, this is the reconstruction using the 25 years of data at once. And you see that it's quite smooth. Okay, so it concentrates on long time, large scale features. And using only the 2 last years of this test, we were able to have a better reconstruction using the DINOF, which is similar to this one, I would say. But yeah, then the error was smaller for DINCAE. Some example again. Yeah, you can see sometimes some artifacts are still appearing, but yeah, again, you have so the initial data, the extra clouded data, and then the SST reconstructed by DINCAE and by DINOF. Yeah, so this is available. So DINCAE is also available in GitHub. So you can just go and download the code and use it for your purposes. So that's there for you. There is also some new developments that will be published soon, I hope. Up to now, everything that I showed is for gridded data. So level 3 data, SST, chlorophyll, winds, whatever variable, but it doesn't work. So DINOF or the DINCAE, as I show it up to now, doesn't work by gridding data. So if you use tracks from altimetry, with DINOF you cannot obtain a gridded field. But in DINCAE we have been developing that, and that will be, as I say, available soon. And yeah, so this is the validation coming from that gridding of the data, which is I think it's go too much in details here, but yeah, the validation is showing that we are able to provide an improvement and a good reconstruction and reading of the data. So just some quick conclusions so that I have time to show you the notebooks. I have presented DINOF, which is a method which is reliable for filling missing data. It has been used for many years, and it has been, we have several applications that have been added or that can be added for data quality improvement. DINCAE, it's a convolutional autoencoder. It's also for filling missing data based on a neural network. It has been developed for only a few years now, but it's really showing a very nice promise. So we are really very happy of having this new tool in the GHR. So in fact, what is funny is both methods aim to compress the data into a low dimensional subspace and then reconstruct the full field from this. So that's the funny thing is that they are really doing the same kind of analysis, the same kind of rational, but just using different tools, UFs and neural networks. Yeah, so now what, DINOF or DINCAE? Well, as I say, DINCAE shows a lot of promise and adaptability to new challenges like this unstructured data, so it's really nice. Now you need a powerful computer with a GPU, so you won't be able to run DINCAE just on your laptop, which is something you can do with DINOF, in fact. And then DINCAE, again, because you need very long time series, so for neural networks, you need that. It's only able to work on very small regions. You cannot do a full base in South Atlantic or whatever with DINCAE. It's just too heavy to handle that. Okay, and then DINOF, so it's the tool that we've been using for like 20 years. And it's still very valid. I still use it all the time and still giving nice, very nice results, and can do a large region with a few computer resources. So really, you can use it in your laptop. And sometimes short time series are very often enough. You don't need 20 years of data. And in fact, it's more often than not within 20 years of data is just too much. You need to cut that down. Now, as I said, DNOF is available as well, so you can look at it in GitHub. You have the code in there, just for download as you want. And then I prepared some notebooks, okay, so that you can try. I will run them myself here now, but you can just download them and try them at home. And then if anyone has a question, just you feel free to contact me, and I can help. I can answer any questions. The notebooks, as I said, are written in Julia, but as if you are not familiar with that, I will anyway explain you the notebooks right now. Okay, so a few words for the notebooks. I have used level 3 SST data from Siemens. Again, I use SST because that's my default variable, but you can use that with any other variable, right? Chlorophyll or turbidity, whatever. But yeah, the examples are for SST, multi-sensor level 3 from Siemens. I took the multi-sensor because, well, they are, merging several satellites, so you have less missing data. So that's always nice. And the fields are very, I mean, they are very nice and well, so they are very useful. Now you sometimes find yourself, you have not a multi-sensor, but just a mono-sensor, so just one sensor. It's still doable, it's still, I mean, you can still use. But I mean, if you go to Siemens and download a 3-dimensional data set on a specific region of interest, you download that data, you could use the notebooks with that data directly, okay? So you would need to change almost anything. So the notebooks are ready to work with this data. Okay, so that ends the presentation. Maybe I will take questions, slowly. I will maybe take some questions for the Dinkai part also. I went quite fast, in fact, but yeah, that I wanted to have time to. It's possible to use Dinkai without NVIDIA. Yeah, you need a GPU really to run a neural network. So I mean, it doesn't have to be NVIDIA, but you need a GPU. Yeah. What about deterministic and statistical methods such as Kriging, Spline? Have you tried them? Yeah. I have tried. I mean, for in situ data, you can use approaches like Kriging and Spline, and you could obtain very nice results. Now, for this kind of methods in which you have a lot of data, a lot of scales, and a lot of variability, I do think that EOF methods or the DNOF or optimal interpolation are better suited. So I would, yeah, it's you will end up with fields that are not smooth or not. Yeah, I would recommend to go to a little higher order method. How about the in this image of Dinkai fields, we saw an output field that is complete and differs from the input data locations where data was available. Means that rather than gap field, we have a completed synthetic field. Yes, and that's the same also for DNOF. Okay, for when you do a reconstruction, you can reconstruct only missing data, or you can do a full reconstruction. Okay, so you can leave the initial data as they are, and then just reconstruct the parts that are missing. Now, the problem is that you might end with a gradient at the limit between missing and non-missing. You will have something non-real. And if your initial data has noise or bad data, etc., this will be retained. I mean, this will be there in the end. So typically, I mean, you can retain the initial data if there are very good quality. Why not? But yeah, I do always reconstruct the whole thing. Yeah, it is a full reconstruction. But I mean, yeah, you can do both. Mm-hmm. Have you tried running Dinkai on Google Colab rather than using your own GPU? I have. We have been trying to do some tests. I mean, we have always used our own GPUs so far, but also because you need really a lot of tests and going back and forth, etc. So yeah, instead of expending a lot of time resources and GPU resources on the cloud, we have used our local machines. But yeah, they can be of course used. Yeah. Mm-hmm. As you said, there were heavy wind in the region. Did you include wind data in the neural network? We didn't use wind in this case, but we could, of course. We could add it as a new variable. And yeah, there are multivariate approaches that can be very useful. And in fact, the multivariate approach can be also used in DNOF very easily. So it's just a matter of putting more than one variable together and use them all together. But yeah, multivariate is always, it was a nice idea. You have more data, more information, and then you help the interpolation. Mm-hmm. Are these results published? Yes, so for, I guess it's the Dinkae. So the ones that I show with the Ligurian Sea, that's already published. The other one is something we just submitted this week. So they will be available, I hope, soon. Okay, nice. Okay, so now for the test, we still have more or less half an hour. Maybe I have to run a little bit, but we'll try. Okay, what I'm going to do is to share my screen again. Where is it? Here. Yeah. Okay, so I have started the Jupyter notebooks. I will just go. So again, they are available. I will show again the link later. Okay, but now I will just show you what it is in there. There are 3 notebooks. I have more here because I've been developing things, but there is one notebook which is called DNOF pre-processing. Then is DNOF, Adriatic long, and then DNOF results. Okay, so there is a pre-processing, preparing the data, running DNOF, and then looking at the results, 3 notebooks. So I will start with the pre-processing. When you open it, again, it's in Julia, okay? I have added some text to explain, etc. But yeah, of course, you can always add more things. So this notebook, so I will start just by executing, reading some libraries that I need. I don't know if you're familiar with Jupyter notebooks, but you can execute each cell separately. So I'm executing the first one and it's running because it's showing an asterisk. And then we'll go to the next one. The next one, I have put the data that I'm using in this notebook are also there for download. If you don't have them, now I'm not sure if they are in the package, but if they are not in the package, the same exact that is used in this is download. And it's exact directly the file that I just downloaded through Siemens. Okay, no, I didn't modify anything. Well, I just put a name. Okay, so this cell here will just download the data if they are not yet in the folder. Okay, in the local file. I'm reading, so it's Meteo France, in Europe, SST, level 3 multi-sensor, okay? And it's a 1 year of data of SST in the Adriatic Sea. Okay, so next thing is reading the file name and extracting the value, the variable sea surface temperature, the time, the latitude, the longitude, and the source of SST. And I will explain that in just a minute. So I will just read this. So I'm reading, as I say, SST, time, lat, and long. And then I'm doing this in here. I will explain it by showing later something. Okay, I'm removing some of the sources of data. As it is a multi-sensor product, it contains several satellites, and some of the satellites, which are microwaves and the Severi sensor, they are coarser, and they do have some weird, I would say, or strange representation in the data. They are coarser, and you can see that. And you might find these artifacts at the end. So I prefer to remove that because in the Mediterranean you have enough data without using this. So we don't use it. Okay, so I read the data. It's a matrix which is 400 by 300 in space and 365, so one full year. Okay, I will just show the initial and end time. So the first time step is 15 October 2020, and the last step is 14 October 2021. So you just see that I just downloaded this a few days ago. Okay, we'll do a quick visualization, and I will show you this effect of the cursor sensors. Okay, so this is a snapshot. I just plotted. So this is the instance 90. Okay, whatever the date. I'm just plotting with a p-color, lone and latitude, and then the variable that I read at the beginning. Okay, which is in Kelvin, and then the one in which I already removed the cursor sensors. Okay, so I'm doing just a p-color and then putting some aspect ratio in there to just have the correct aspect ratio. So the initial data, you see these lines. I don't know if you can see that. I will make this a little bigger. So you see these lines in here. This is because the cursor data are having this effect in there. And in fact, you can see that as well. I don't know if I changed, you can still see, you see the presentation now? Hayley, do you see the
yes, we do. It's
presentation?
Good.
So you see these little dots in here. So this comes from the compositing example that I show. These little dots in here, this is data that are cloudy in the infrared, but they are filled by microwave, which are cursor, but they do it like this. Okay, I mean, everyone does as it wants, but I do feel that this includes some structure in the data, some square structure in the data that reconstruction techniques like DNF and DINCAE will just retain, and that adds noise to the final. So because there is enough data, I don't need microwave. If I would be in a region with a lot of cloudiness, etc., I would be interested in having microwaves because they have more data. And they have better coverage because they are not affected by clouds. But in here, I think it's enough. So I will remove that so that I don't know if you see the difference. Here, I don't see anymore these lines. Okay, so that's something like I recommend to do, but it's not necessary. If you don't want to remove that, then you just have to comment these lines in here, these 3 lines, and that's all. Okay, so that's the SST data that I downloaded. I don't know if you already can see more or less the Adriatic Sea in here. And then we are going to do a little pre-processing, as I said. This is a snapshot. Again, this is a snapshot number 2022, 225, whatever the data, I don't care. It's just to show you the full regions because it's a date which less cloud. The Adriatic Sea. And then you see that you have part of the Tyrrhenian Sea and also part of the Ionian Sea. I'm not interested in those parts, okay? So the best thing we can do, especially if we have parts that behave very differently from what I want to study, is just to remove that from the data, okay? I wouldn't use, I mean, I'm not interested in the Mediterranean Sea, so I won't include it. And that also will make my analysis faster because I will have less data. So I'm gonna mask this part and this part, the Ionian Sea. And now this is done by hand, okay? So this is something that you just have to just remove from the data initially. So it's just a trial and error with the indexes, okay? So in this case, I just took index 1 to 205 and 1 to 225, and then put that to not a number. And again, for the other things. So I just masked part of and then that's the final matrix. Okay, I don't have the Tyrrhenian Sea anymore, nor the Ionian Sea. But again, you decide what you want to keep, what you're interested. But if there is a part that is not interesting for you, and yeah, then you can remove that and then concentrate on the region you're interested. Okay, the next cell will just transform the time value into a date. Okay, this is this line here. And then from the SST, I will create a land sea mask. That will be a mask that is 1 over land and 1 over sea and 0 over land. And this is just to tell DNOF which are the points that I want to reconstruct. So I don't want to reconstruct the land because there is no SST over land. And I want just to do a reconstruction over sea pixels. So that I just do an average in time. And then every point that is missing, that is not missing, sorry, on average, is put to 1. And then the rest is put to 0. This is a very first guess for a mask, okay? Just what is not missing all the time will be sea, and if it's missing, it's land. And from that mask, land sea mask, I will calculate the amount of missing data that I have in my data set, okay? Because then I can concentrate on just the sea points, how much missing data do I have? And that's what this coverage function is doing. And yeah, this is the time series. So you have 365 days. And this is the percentage of missing data. I could have added some labels, sorry. And then you can see it's very variable. So you have days with 10% or even 5% of missing data, but then you have days that are close to 100% of missing data. So days that are almost all the time missing, okay? Now, what I do always is if you have days, individual days that don't have any data at all, then it's better not to use them because they will just add difficulty to reconstruction, and you will end up with an average reconstruction for that day. So whenever an image has more than 98, 97, this is something you can also decide, but 98 is like a default. Less than 98% I mean, more than 98% of missing data, then I don't use that for the reconstruction. So I won't have a reconstruction on that date, which is, yeah, that's how it goes. Yeah, you can later, once you have your reconstruction, you can interpolate linearly the days that have been left out if you need really those. But yeah, otherwise I will just remove that. And from the 365 initial image, I have now 355. So, okay, it's not the end of the world, I would say. It's just 10 images that are just, I mean, there is less than 2% of valid data, which is very, very, very small. And then I will do the same thing for time. So if a pixel is missing in time more than 98% of the data, then I will also mask it as land. And you will see now, so this is an average value, and then cover percentage of missing data. So you can see that there is a lot of missing data near the coast, okay? That's normal also in this region because so many islands, etc. So it's more difficult to have data in those regions. But yeah, you have missing data, especially around the coast. So those pixels, just we are here at the pixel, individual pixel, those pixels that are missing 98% of the time, I will just say they are land and I won't reconstruct them, okay? Again, this is something you can decide yourself, how much you can go with this 98%, okay? But that's something, yeah, so that's, yeah, there are pixels, the maximum is 99.7, so there are pixels that are 99.7% of the time not there. So I will remove them, okay? So I will remove those pixels, will be out. And this is my mask, okay? So did you lose me a while ago or?
Just very briefly, I think, there, Aida.
Sorry, I just saw, okay, so I'm back.
I think it's okay. Yeah, you're back. And I don't think we missed a lot. I think it was a good time to have a break.
Okay, I will just share again. Sorry, share. Yeah, so I was talking about the missing the missing data in space. Did you hear that? So I'm removing all pixels that are just more than 98% of the time are not there. I will just put them as if they were land. I will classify them as land, and then I won't reconstruct those pixels. And that's the final mask. Okay, one on points that I want to reconstruct. There are C points that I want to reconstruct, and blue is 0. There are points I don't want to reconstruct. We'll do a last visualization. And yeah, that's one example of a date with some clouds. You can see so the cold temperatures going in the north and then flowing in the western basin, and warm temperatures going up. So that's good. Now, I didn't do it in here, but you could also fine tune the mask. Okay, if you have a lagoon, there is a little lagoon here in the Gargano Peninsula that it's showing high temperatures, like this, dissociated with the rest. So if you want, you can go and fine tune and remove some more data because you are not interested in this lagoon, etc. But I mean, it will be the same procedure as before with the Tyrrhenian Sea. Okay, so you decide which are the points that you want to reconstruct. So that's the data we want to write on the disk. I will just make sure I don't have the data. Wait, sorry, 1 minute. No. Okay, this. Okay, so I will write this cell. What it's doing is writing the final variable in a file. It's a file I call SST level 3 Adriatic long because it's 1 year. Okay, I did a shorter test to see if that was enough, but I just kept it long. And then it's writing, so SST time, the mask, latitude and longitude. One last thing we need is to create the cross-validation points. And as I said, I do that using clouds, okay? And that's what this routine is doing. It's adding clouds from a cloudy image, and it adds to clean images so that we mask 2-3% of the data, and then we can calculate the cross-validation error. So this routine takes the SST and the mask. This is where you want to write the results, and then the number of images you want to mask with a cloud. Okay, so we'll just run it and see. Yeah, so I have added, so 0.84, so I have 0.84% of missing data extra that I will use for cross-validation. This step creates a file in my system. I will change the my screen. Yeah. So this so I have written the file, so the SST level 3 Adriatic long in my computer. And this last step creates a file that's called cloudsindex.nc. If I generate again, if I rerun again that cell, this file will be overwritten. So what I do typically is to just move the file to another name so that I keep it for, I mean, that I don't erase it without knowing it. Okay, so I will just move. So this is the cross-validation points, which are in the form of a cloud. Okay, so now we have ended with the pre-processing. And now we can run DinoF. For that, we have the other notebook, so DinoF Adriatic long. And in this file, we prepared all the data that is needed for DinoF to run. Okay, we need the data. the name of the data set, so SST level 3 Adriatic long, so the one we have created that we have removed the points that we don't want to reconstruct, and the name of the variable SST. So that's something you find when we wrote the data, we call it SST. Okay, so that's the variable we want to reconstruct. Data, we need the mask, which is in the same file, but just the variable is called mask. We need the time, and this is for the filtering. Okay, you remember I told you that we were doing this filtering. And so we need the time, which is in here, the same file, but the variable is called time. And then you will need two parameters. These two parameters are the strength of the filter and the number of iterations. And in order to know to what does it correlate, I mean, to what is the length of the filter, you just say 2 times pi times the square root of alpha times numit, and that will give you the length of the filter. Okay, if I keep 0.01 for alpha and 3 for numit, I will have a 1.09 filter. Now I just increased it a little bit in here, 0.1, but this is something you can really just try to see what the effect is in your data set. Sorry, this is something I should have changed. The rest is really just so. This is the maximum number of modes you want to compute. This is just to avoid that it keeps computing for hours, because if the minimum is at 10 UFs, it doesn't need to compute more than 20 or something. Then the first UF that we will calculate, it should be 1. Okay, it's just you change that just if you want really to start in higher order UFs, but other than that you just keep it to 1. And this is just a number that has to be higher than this one, which yeah. Then the threshold for the convergence in the SVD, all the rest of the parameters, you just leave them as they are. This is the number of iterations allowed to obtain the convergence in the UFs. Again, this is typically not reached, so it will just stop before. You can leave it. And then the precision in what does it mean, convergence? So convergence is no more difference than 1.0 to the -3. So when the change between iterations doesn't change more than that, then you can stop. You have reached convergence. Rec 1, this is answering one of the questions I got. If you want to reconstruct the full thing, the full matrix, then you put that to 1, it reconstructs the whole thing. If you want to retain the initial data as their value, you can put the rec equal to 0, and then it will just reconstruct the missing data. And then, yeah, I keep it to 0. And then this is the file that we have created at the end, the cross-validation points. I will just verify, yeah, that I name it like this. So you put here the name of the file that you created in the last step in here. So this last set. Normalize. If you use a multivariate approach, if you use more than one variable, you normalize your data. If you're using one variable, you don't need to normalize anything. And if you want to obtain the EUFs at the end, which I think it's nice, you can put 1. If you're not interested, you put 0 and you don't have the SST. The output will be written in a folder called Adriatic long. So if you're using this notebook, you should create that. And the results will be written in the folder Adriatic long in the file SST level 4 DNOF Adriatic long.snc in the variable SST field. And then this is the EOFs. If you want them to be written, then they will be written in this file. So we just execute this to have this data created, and then we run DNOF. This is just a line. You have to point to where you have your executable, which comes again with a little package that I put to you. And this is the file that we just created in the previous set. Okay, this is the name. If you go here, right up there, yeah, this is the one, the name that we gave to our file. This is the file that contains the data that the DNOF needs. So it will just execute this, and we'll have the output. It starts calculating, so now it's calculating. It gives you first some information about the data you entered, so how many modes you want to compute. You are not to normalize the input matrices. You will write the results in here. The file names you entered are these. The init file name is this one, some statistics. So this is the size, the number of land points, the size of the file, the average value, 19 degrees, and the standard deviation, 5 degrees. And then once you take out land points, it's 38,387 points per day. Okay, so that's the C points that are going to be reconstructed. There is this filter inactivated, and in fact we have 37%, 38% of missing data, which is not very high. And yeah, that's the missing the cross-validation data. And then once it has all this, it starts calculating the EOF modes, and then it will obtain some results. While this is running, it will take just a few minutes, but because we are running out of time, I will already show you the results, which are already in there. In the results, I just read the data and make some plots. Okay, so it's just reading some libraries, and then reading the initial data, the level 3, and the reconstructed data. Okay, so we just read that, we read the time, and then we do a little plot. So there will be 2 plots. I will just take instant 90, so that's something you can change. And I plot first the initial SST, the level 3, and then the reconstructed SST. And it's just calculating now. Yeah, I have maybe asked too many to the laptop at once, but I mean, just to show you. So this is still calculating, and I will. Yeah, so this is just one snapshot. Yeah, I chose one with a lot of clouds, but yeah, so this is the initial data and the reconstruction. So this notebook here will allow you to look more in detail the reconstruction. This is an histogram, which is always nice to verify that our distributions are correct. So yeah, you have the distribution of the initial data. It's 2-modal. It's a funny one. This is the northern part, which are very cold, and then the southern part, which is warmer. And then in situ, the DNOF data has the same distribution, but of course it has more data because it's full. It has no missing data. And then there is also a time series in here to show you the SST. So this is the initial data in red and the reconstruction in blue. Now you will see that it looks like there is some variability lost by the DNOF curve because it's blue. And yes, there is some variability that is lost, but you also have to remember that some of these images are averages over subregions. So maybe there is only the northern part of the Adriatic Sea or only the southern part. So the average will look like colder or warmer than if you take the full. So always a full reconstruction will look less variable because it's comprehensive. So it takes the whole basic. But yeah, so that's the time series, and this is another example. Yeah, that's the same thing again. And there is another cell showing you the EOFs. Okay, so we read here the EOFs. I just wanted to show if maybe you want to have a look at one of the EOFs, for example. We'll just take a look. Yeah, so this is the first EOF. And again, so you can see that the spatial variability is showing. I want to ask you, sorry, I'm going to change the sign. It's minus, but I think we can put it here. So you have this region, which is very well separated from the rest. Okay, so the northern region and this current that goes to the south is very different to what is in the other part of the region. So you have this annual cycle, and the intensity of the annual cycle will be higher, will be larger in this shallower part in the northern Adriatic. Okay, so it will warm more and it will cold more during the year. If you change this to number 2, you will see the second EOF, etc. So this is the second EOF. Okay, so these are the results obtained because I already run DNOF before. Okay, so this is now running. The first mode is there. So you have reached convergence for the first mode, and it will continue to compute for a few minutes, less than an hour if I remember correctly. And then at the end, you will have the full year SST reconstruction for the Adriatic Sea, and then you can run the results. So but this will keep on running for for more or less 1 hour because it's 1 year of data. Okay, so that was very fast, but I think we have to end by 3. But the 3 notebooks, again, they are available in here. So you have a little package in there in which you have the notebooks and all the routines you need to run, and also some executables, so a Windows executable for Windows and a Linux executable. And you can just use that to run the notebooks. So is there a question or many questions?
Thanks so much, Aida. That was brilliant and so much to take in, but so very detailed. I mean,
we could have done a couple of hours more, maybe.
Definitely. I think the idea earlier to have a course on this might be a good idea. Maybe we come up with some idea and we can throw it at some different data sets and try some land, try some atmosphere stuff as well. So maybe much more to do. But thank you so much. Let's see what questions we've got.
Yeah, so the notebooks are there just to guide you, but they are just pre-processing the data. So if you prefer to pre-process the data, doing more or less the same thing I'm doing in another part, in Python or whatever, you can do that, of course. DNOF runs in the computer. So I just put that on a notebook just to frame it. But DNOF is just running on the computer, so you can just run it on the command shell. The executables for DNOF are provided in the little zip that I provided. So you just do the pre-processing, doing the same thinking that I did in the notebook. So taking into account that if some days are too cloudy, maybe it's better to take them out. If some part of the region you want to reconstruct are also too, you don't need them, then you maybe remove them, etc. But you can do the pre-processing in any language, in any program. Then you can run DNOF from the command line, and then you just visualize the results, whatever you want. One thing that I haven't said is once you run DNOF once in your data or in this data, you will see that it retains X EOFs, I don't know, 10 EOFs. You look at the results and they look too smooth for you, then you can go back to the DNOF preparation, the DNOF notebook or and play with the alpha and numit. If you play with a filter, you will obtain different number of EOFs, and you will obtain reconstructions that maybe are more variable and that better for your purposes. So that little filter, these 2 parameters there, allow you to obtain sometimes more EOF, less EOF, and then you just try and see whatever fits you better. Okay, if I want to run a gap fill operational, will I have to run my entire available period to fill only the most recent day? That is yes. Okay, I will share my screen for 2 minutes more. Oh, yeah, can I share my screen? Yes, and I will show my screen again. I will show you this this operational thing that I have. This operational DNOF. So every day I have the latest SST downloaded, and it's added to a 6-month data set, and then I run DNOF and obtain this reconstruction. I do it twice because I run DNOF, I remove outliers, and I run DNOF again, and then I plot the results. Everything is done automatically, and it takes 2-3 hours of computing time. So it's not very it's not very heavy, I would say. So it's better to run again the full 6 months because you will add the new variability, the new things that happen at the end. If you use your EOF basis that you had for 1 week ago, it won't reflect what is happening now. So it won't be a good idea, I would say. So it's better to use every day the latest data. Yeah, so that's for operational applications. So yeah, that shows it's 2 days ago. I have to update this. But that's 2 days, and then you can see that, yeah, clouds move around, and then you have the reconstruction in there. But yeah, I would always use the latest data possible so that the EOS reflect the latest variability in your data. Okay, so next question.
Great. Do we have any more questions?
Okay. Then yeah, so please try it. Yeah, let's see if you have any question or anything. I would be happy to answer them. Yeah, and let me know. I would love to have some feedback on how the notebooks work. So that's always welcome. And thank you everyone for attending.
Great. Thank you so much, Ada. That was really great. And thank you everybody for being so engaged and asking questions. I really do hope you will try the notebooks. As we've said, we'll share the recording and the details with you through the training.eumetsat.int page where you registered for this webinar. And please, if you can, do fill in the evaluation that's on Slido now. You can go to the same link you're at before, and the link's been shared again in chat. We really value all your feedback, and it really helps us to develop these webinars and other events based on what it is that you, the users, need. So that's all from us today. Thank you very much, and hopefully we'll see you again at another short course in the future. Yeah. Thank you. And thanks again to Ada again.
All right. Thank you, Hailey. Bye-bye.
Bye-bye.
Thank you, Aida.
Thank you, Rosa. Thank you very much.